particle of mass m is accelerated from rest by a resultant force of varying magnitude that acts in a constant direction. The kinetic energy E of the particle increases with time t, according to the equation E equals kt, where k is a constant. Which expression gives the resultant force on the particle at time t? So, we want to find out the resultant force, which is F equals ma. And we can also write this as the rate of change of the momentum. So m dv by dt. So I think a natural candidate for our procedure here would be to find the velocity and then differentiate with respect to time and then multiply that by m. So let's try that. We have the kinetic energy is half mv squared, which for this problem happens to be equal to kt. We could find out that v squared equals 2kt over m, which gives v equals square root of 2kt over m. And if we differentiate with respect to time, we get, this is a t to the half, so we're going to get a half on the outside, and then 2k, the t will become a t to the minus a half, or the root t becomes t to the minus half, so we'll get an mt here. And then time, well, multiplying everything here by m, we get m dv by dt equals, well, the half and the 2, if we bring the 2 inside, this is a root 2 squared, so the 2 will now go on the bottom, and then because we get m, m can be written as square root of m squared, we get mk over 2t. And this is at time t equals capital T, so we get the answer of D. So the answer of D is square root of mk over 2 times capital T. Now, a slightly more elegant solution would have been to use one of the forms of the kinetic energy which I really recommend using for NSAA and ENGAA. So we have p squared over 2m. Really useful in a lot of questions to use p squared over 2m rather than half mv squared, and use it a lot in university physics. So get familiar with this form by substituting v equals p over m into your kinetic energy equation to get this form of it. So you get p squared over 2m equals kt. So p equals the square root of 2m kt. And then we know force is dp by dt from Newton's second law. So because this is a root t, we're going to get a half root of 2mk over t. And then moving the 2 inside as a root 2 squared, so from the half we get root of mk over 2t. So you get that same answer, and this one is a lot more, well, a lot quicker, a lot more elegant, and I think just an all-round better method. So this is the one I would have gone for when doing this, because p squared over 2m just seems to be always a really good option when doing NSAA or ENGAA questions. Now, the next method I'll use is not something I would recommend for this question, but I would offer it up as a possible way of doing it if you get familiar with how forces and kinetic energy are related. We know that the work done, so let's say the change in work done, is force times change in displacement, so I might call this x, for example. So force is the gradient of the work done. But we can also see this as equivalent to saying force is the gradient of your kinetic energy. So let's say E, put subscript K over delta X. because when you transfer energy, let's say you do work on an object, in the absence of other forces, the net force, well, the net force or the force that you're dealing with here, multiplying this by the displacement converts this energy into kinetic energy. So the process of doing work transfers or kind of develops a kinetic energy in the object. So force can be seen as the rate of change in kinetic energy with respect to displacement or position x. So sorry, I should say position x, because displacement is the delta x, or changes in position. So what that means is that if I wanted to get the force from E equals kt, I could just do dE by dx. And then doing this on the other side, we get k, and then this will become dt by dx. If you notice this, dx by dt is velocity, so dt by dx must be 1 over velocity. So this is using dx by dt equals velocity here. So if I want to work out the force, all I need to know is what the velocity is as a function of time. So I can just use half mv squared equals kt, using what we did in the first part, which makes this method also quite long, so not as nice as a p squared over 2m method. But again, just showing this so you can see an alternative method. We get v squared is 2kt over m, so v is square root of 2kt over m, just to rewrite that. Substituting this into here, we get k times square root of m over 2kt. And because k can be written as square root of k squared, we can write this as km, or mk. Don't know why I chose to write it km when the convention has been mk. And then this is 2t on the bottom. So this is an alternative method, not something I'd encourage here, but it's a very useful way to think about how kinetic energy and forces are related. So this is useful if anyone was deciding between the NSAA and whether to do the physics aptitude test for Oxford. It's a very common relation to see that force is related to kinetic energy. So I'll just show here that we know the kinetic energy that an object develops will be the force times dx, the work done, between, let's say, x is 0 and some final position, x equals, let's say, capital X. But what we can choose to do here is, if we write this as m dv by dt dot dx, we can choose to, in a almost a legal maths move, so you can get a mathematician to justify it, so I won't bother with the rigor here, but we can move over the dt to the dx term, and we get here m dv and then dx by dt. Dx by dt we can say is equal to v. So we get that kinetic energy, which comes from the work being done on an object, is equal to mv dv, where we get from v is 0 to maybe v is some final velocity. So what I'm going to do here is I'll just change these v's to a v prime. V prime doesn't mean dv by dx here, it just means some variable v prime that's going between 0 and the final velocity v. I'm just changing these to v primes. So when we integrate mv prime dv prime, we get half mv prime squared between v and 0. Substituting this in, we get the equation that you all know and love, a half mv squared. So this is how you can relate the force and kinetic energy. So half mv squared equals a kinetic energy, and it comes from the work being done on the object. And then a final relation that's useful, again, you don't have to keep watching from this point, because this is not so relevant to the problem that we've been doing. But if you differentiate kinetic energy with respect to time, you get d by dt of a half mv squared. And then using implicit differentiation, we get this as mv dv by dt, which is equal to mv times acceleration. So we can rewrite this as ma times velocity. And then you see that the rate of change of kinetic energy, which is power, so how much power is being added to the system, is equal to MAV, so this is force times velocity. Again, the common way of seeing power equals FV is just differentiating the work done with respect to time, so F times dx, then divided by dt, you get F times V. But these are just multiple ways of getting to the same answer, so it's quite reassuring that everything you see here reinforces the other bits of content or other bits of physics that you might have learned over the course of your education. If you have any questions on these things, let me know in the comment section, but hopefully this all made sense.